Okay, good morning. Last lecture. Okay, I'll just get going. So today we'll be in rather the style of last time. So reasonably quickly, and in fact, probably almost certainly too quickly, describe a bunch of stuff. Okay. So to motivate the discussion of much of the lecture today, let's look at some simple constructions. So here I'm going to just talk about sets. Okay, so I have sets A, B, and C. They have no topological structure. They have no differentiable structure. I'm just going to describe some mappings that are associated with mappings of sets. Okay. All right. So here's the list. So if phi is a mapping from A to B, and mappings from A to B are going to be written like this. Okay, so this is simply the set of mappings from A to B. Okay, that's shorthand for that. So if you have a mapping from A to B, this induces a mapping from the set of mappings from B to C to the mappings from A to C. And it's just a simple composition. So if psi is a mapping from B to C, from B to C, then I get this mapping from A to C obtained just by the composition. Okay, and it's, I think, helpful to just sort of write everything in a little sequence here, right, like this. All right. And then so this is composition on the right. Okay, so psi is the variable in this equation, and the composition with phi is on the right. And similarly, if I have a mapping psi from B to C, like in the diagram over here, then I have this mapping from the set of mappings from A to B, okay, from A to B, into the mappings from A to C. And again, it's the same composition, just the variable is different now. So here the variable is psi, here the variable is phi. Okay. All right, so these are just composition mappings. You can also consider the joint composition mapping. All right, so now both of the things are allowed to be variables. So I have phi like in the diagram and psi like in the diagram, and I compose them, but now both of them are allowed to or to be thought of as variables. But symbolically, the mapping looks the same. It's just well, symbolically, all of these mappings look the same. The only thing is, what are you regarding as a variable, and what are you regarding as fixed? Okay, so composition mappings, good. Evaluation mappings. Okay. So I take a point, fix a point X and A. Okay. Then I have the mapping, which is evaluation at X. Right. So this takes a mapping from A to B, gives you a point in B by the obvious rule. You just it takes a mapping, phi, and evaluates it at X. Right? Evaluation mapping. And similarly to the discussion above, what are you going to consider as variables? Well, here the variable was the mapping phi, but I could also consider X to be a variable. So upon doing that, I get the mapping EV, okay, without X being prescribed, but it's the same mapping. So now it takes a mapping phi and a point X and gives you the corresponding point in B. All right, evaluation mapping. All right, so this is a blizzard of mappings to start things out with. Okay, so there's also a bunch of constructions that go along with mappings on products. Okay, so I have a mapping phi on the product A cross B, taking values in C. All right, so then you have just two simple mappings here. You get a mapping phi sub X, okay, obtained just by fixing the value of X in phi. Okay, so it's just defined by the simple formula. And similarly, if you fix some y, then you get this mapping, which is now a function of x. So those are simple ones. You also have a mapping, phi upside down wedge, check if you want to call it that. And what this does, okay, so remember phi here is a mapping from A cross B into C. All right, so corresponding to that, I'm going to have this mapping phi check, which takes a point in A and gives me a mapping from B to C. And it does so. So, again, if you give me this thing and tell me that you want me to define a mapping like this is the only way to do it. So I take a point X in A, and that's going to give me a mapping from B into C. And here's the mapping. That mapping takes Y into that. Okay, so it's the only possible way to sort of combine the symbols that you have to get the kind of object that you want. Okay. All right, so this one takes a mapping on a product and gives you a mapping with values in a space of mappings. All right. And then you have this other mapping, which I call phi. This is a dagger. Okay, LaTeX dagger. And this one is a bit like the composition mappings that I had above. In fact, we'll see that it has some relationship to them. But it takes a mapping from, so again, remember here what phi is. Phi is a mapping from A cross B into C. Okay. And what I get out of this thing, phi dagger, is a mapping from the set of mappings from A into B to the set of mappings from A into C, and it's defined like so. Okay, so I have a mapping psi from A into B, okay, and I get a mapping from A into C, and it's defined by this formula, right? So you see it just fixes the value of x just slides into the first variable of C, and then the second variable of phi, and that should be, sorry, of x, or sorry, psi of x. I have a y. All right. Okay, and then the second variable, which I would call y, is obtained by putting in the value of psi at x, right? So again, just some mapping. Okay, and then you have a mapping which kind of undoes this mapping. Okay, so this one takes a mapping on a product and gives you a mapping with values in a space of mappings. Well, now I'm going to kind of build an inverse of that. So I'm going to take something like this and I'm going to produce something like this. And again, there's only one way to do that. So I take a mapping psi. Again, that's just like I had here. Then I retrieve a mapping on the product by this formula. And so again, there's only one way to assemble all the symbols you're given to give you the kind of object that you want. So I want to evaluate psi wedge at points in A and B. Okay. All right. But psi is a mapping from A into the set of mappings from B to C. Right. So this thing will be a mapping from B to C. So I evaluate that at Y. And that gets me something in C, right? So why are these things interesting or important? Well, we'll see that as we go along. And we'll really mostly see it with some examples that we talk about at the end of the lecture. Okay. So on sets, these mappings wedge and check are inverses of one another. Okay, like this. Okay, on sets, everything is nice. Okay, and because check is the inverse of wedge, and wedge is the inverse of check, then that means that the mapping, which sends phi to phi check, that should be a bijection because its inverse is phi wedge. Okay, so what does that mean? So that means I have a bijection from the set of, all right, so remember in my original definitions what phi was. Phi was a mapping from A cross B into C. Okay, so that's the set of mappings from A cross B into C. And then it maps it to what? It maps it to a mapping from A into the set of mappings from B into C. Okay. And I think I have that incorrect. So it's the set of mappings from A into C to the B. So it's C, oops, C. Okay, so it's C to the B to the A. Okay, like that. Sorry, got that backwards. All right. And this mapping, as I have just said, is a bijection in the case of sets, right? And this correspondence of mappings from products to mappings in spaces of mappings, according to this rule, this is what's known as the exponential law. And so you see that it has, it has a this property of C to the AB is the same thing as C to the B to the A, right? That's a property that is possessed by the exponential function. So that's why this is called the exponential law, right? And that's sort of why this notation of C to the B being the mappings from B into C, that sort of reveals why this thing is called the exponential law, right? And then there's a couple other, there's some relationships between these things. I have a feeling yeah, I think it's right as it is. Okay. All right, so there's some other relationships between these various mappings. Okay, so that's all just mappings between sets. So, which is not a very interesting context in which to talk about very much. And in this course, we've been talking about mappings which have various between sets, which have various properties, and then the mappings have various properties corresponding to the properties of the sets. And so, for example, the sets might be not just sets, but topological spaces, and the mappings might be continuous. Right? And the sets might be open subsets of locally convex spaces, and the mappings might be of class CK for some suitable K. The sets might be manifolds, and the mappings of class CK. So of course, B is a special case of C. Okay. So then if you now go back and you look at all of these constructions, all right, so now instead of C to the B, I'm going to have, maybe in the case where B and C are topological spaces, I'm going to have the set of continuous mappings from B into C, okay? And then that's going to map into the set of continuous mappings from A into C, okay? So first of all, you want to know, is this mapping well-defined? In this case, it's trivially well-defined. So in other words, does it actually take a continuous mapping from B into C and give you a continuous mapping from A into C? And the answer, like I said, in this case is yes, trivially. In some of the other cases, it's not so trivial. Okay, so you want to understand the well-definedness of all of these constructions within the structures that you're talking about. Okay. And then you maybe want to ask, is this mapping, okay, so I have a mapping from the set of continuous mappings from B into C into the set of continuous mappings from A into C, okay, is this mapping itself continuous, okay? That requires me then to have topologies for the spaces of mappings. Okay, and then similarly, if the objects are open subsets of locally convex space or manifolds, and the mappings are of class CK, you want to know about the well-definedness of these various mappings that I just defined. And you also maybe want to know if the mappings themselves are continuous or maybe of class CK. And so you need now, so in this case, for example, again, so let's say there A and B are manifolds. And so I'm going to talk about the set of CK mappings from B into C into the set of CK mappings from A into C. Okay, so A, B, and C are now manifolds. So you want to know, is this mapping well defined, right? So does it take values in here? And maybe is this mapping itself continuous or differentiable between these spaces? And in order to do that, you need topologies for these spaces, or maybe manifold structures for these spaces, right? So that's going to be what we're going to occupy ourselves with for the first little while. Right. Okay, so that's this general problem that I'm describing here. All right. Okay. So all of this is just the stuff that I just said. All right, so now let's actually define structures for spaces of mappings, because I need to do that in order to talk about properties of mappings between spaces of mappings, because that's what my constructions above gave me very often were mappings between spaces of mappings. Okay. So let's look first at this. So, and we talked about this alone at various points briefly. I'll do it a tiny bit more systematically here. Talk about the compact open topology for spaces of continuous mappings. Right. So I have two topological spaces, S and T. And I'm going to assume right off the bat that they're Hausdorff. Much of what I say does not require Hausdorffness, but maybe a couple things do, and I don't want to have to think about when Hausdorffness is needed. If you want to see that level of generality, then this material is presented in the course notes without the assumption of Hausdorff, except when it's needed, because sometimes it is needed. Okay, so everything's Hausdorff. Okay, so the compact open topology for the space of continuous mappings from S to T is defined as follows. So we define a subbase for the topology. Okay, so remember what a base for a topology is. So a base for a topology is a collection of sets, so that every open set is a union, not finite or countable, but an arbitrary union of those base open sets. Okay, so that's what a base is. A base is a collection of sets, open sets, whose unions form the collection of all open sets. Okay, and a subbase is simply, again, a collection of open sets for which finite intersections of those things form a base. Okay, so and so you start with finite intersections, and then you can take arbitrary unions of those finite intersections. Right? So that's a base and a subbase. So very often in topology, the things that naturally present themselves to you are not open sets, but either bases for open sets or subbases. So for example, if you have a locally convex space, let's say U, okay, and we have a semi-norm, P, for U, okay, then P inverse of the balls in this semi-norm of radius R, those form a subbase for the locally convex topology. Well, they form a neighborhood subbase at 0 for the locally convex topology. And if I go U plus this, then that forms a subbase for the whole topology. Okay, so the semi-norms for locally convex spaces furnish us with a subbase. They don't furnish us with all open sets, just a subbase for the open sets. Okay. All right, so that's what we're going to define here is a subbase, and the subbase is going to be defined for, you take a K and a U. Okay, so K is compact in S, U is open in T. Okay. And then I consider remember now I'm defining a topology for the set of mappings. Okay, so this It's going to be the set of all mappings which map K into U. Okay. The definition is simple enough. The meaning of it is less simple, but the idea is so the idea is you fix a K, okay, and then you maybe make U small, okay, and then the idea is that mappings are close when they only differ a little bit, okay, and so they differ in this maybe small open set U um, um, uh, across K. Okay, so their values in K are close in the sense that they're in U. Okay. So here's an important example, and one I think that also maybe helps to understand the general definition a little bit better. Let's take my codomain topological space to be a locally convex space. All right. So I'm going to consider the set of continuous mappings from S into a locally convex space V. All right. Now, the compact open topology for this space is easy to define. Okay. Or easy to characterize. Its definition is that, but it has an equivalent easy characterization. So first thing you notice is that this space is a vector space. Okay, so that goes back to your first homework assignment. And then V is a locally convex space, so it has a bunch of semi-norms, which we call them P. And then the compact open topology for this space is obtained in the following way by defining its semi-norms. So I take a P, which is the semi-norm for the locally convex topology on V. I choose a compact set. Okay, so the idea here is that the semi-norm defines my open set U. Okay. And then the compact sets are the compact sets. Okay. And then, of course, given a semi-norm P for V and a compact subset K of S, I define a semi-norm, which I call P sub K, in the following way. So I take a mapping phi, which is from S to V. Then I evaluate P at points phi of X, where X is in K. All right. And I take the supremum of all those, and that gets me a semi-norm. Okay. So you have to verify that that's a semi-norm. Let's think about for a moment about why this thing is well defined. So in other words, why is it finite? Okay. Well, it's finite because I'm souping over K. Phi is a continuous mapping from S into V. And so so the image of K under phi will be compact, okay, because images of compact sets under continuous mappings are compact. So therefore it'll be bounded, okay, and therefore P will be finite when you evaluate it on all values in of the form phi of X, where X runs over K. All right, so at least it's well defined, and it's easy to check that it satisfies the homogeneity property and the triangle inequality. Okay. All right. So one thing that's worth commenting on, because it leads to some challenges down the road, which we'll talk about, and that is that the compact open topology is quite coarse. Okay, so its open sets are maybe bigger than you want them to be. And one consequence of that, there's various consequences, but here's one. And that is that this space, okay, equipped with these semi-norms, is very often not complete. Okay, and it has to do with two things. One, it has to do with the completeness properties of V, but that's what you would expect. You would expect that if V isn't complete, it seems kind of unlikely that this thing is going to be complete. So you should start by assuming that V is complete, but it's still possible that it's not complete. Okay, and that has to do with the topology of S, right? And so this is the first time we're going to see some restrictions on domain spaces so that certain nice things happen. So a theorem is that this space is complete if first S is a K space, and I'll tell you in a second what a K space is, and V is complete. All right. So what's a K space? A K space, S, okay, has the property that for any other topological space T, okay, a mapping from S to T is continuous if and only if its restriction to compact subsets is continuous. All right, so certainly if phi is continuous, then its restriction to every compact subset is continuous. Right. So the interesting part of this if and only if statement is that for K spaces, if phi is continuous on every compact set, then that's enough to guarantee that it's continuous. Right. Lots of spaces are not K spaces. Okay. A common example of a K space or a class of K spaces are locally compact spaces. Okay. It's not true, for example, that locally convex spaces are K spaces. So their open subsets are also not generally K spaces. Finite dimensional locally convex spaces are K spaces. Okay. And so too are their open subsets. Okay. All right, so we see the main point here is we see for the first time there's sometimes you need conditions on the domain space or one of the spaces involved in order for things to be well behaved. And we'll see various other instances of that, some of them coming up just now. Okay, so let's consider all those mappings that I defined above, the composition mappings, okay, the evaluation mapping, these hat and check and wedge mappings, okay? Let's think about when those things are continuous between spaces of continuous functions when they have the compact open topology, okay? So in all of these statements here, my spaces of continuous functions, which show up all over the place, they all have the compact open topology. Okay, so let's see which mappings are continuous. So if you fix a phi, okay, then the composition mapping with phi, which as we saw above is a mapping like so, is continuous. Okay, and similarly, if you fix a psi, the composition mapping with psi, which is mapping between these two spaces, is continuous. Okay, so compact open topologies on all of these guys. Okay. Of course, you'd like to prove that, but certainly we don't have time to do that kind of stuff today. All right, but proofs are, of course, in the course text, which is very incomplete, but the parts of it that are complete are quite complete. The parts of it that are not complete are just not done. Okay. So now we know that the composition with fixed mappings, so fixed on the left or fixed on the right, those ones are continuous. What about the joint composition? Okay, so this one takes a mapping from R to S, which is continuous, and a mapping from S to T, which is continuous, and composes them. Is that one continuous? Well, not generally. It's continuous when the middle guy, okay, so here I have R, S, T, okay. So we require local compactness of that one in order for this joint composition mapping to be continuous. All right. Evaluation mapping. Okay, so now I have a continuous space of continuous mappings from, say, S to T. Okay, and I want to evaluate a continuous mapping at S to get a value in T. This one is continuous, but again, it requires local compactness. Okay, so the domain space of the continuous mappings has to be locally compact. Then that one is continuous. Right. Okay, then there's all these mappings associated with products. Okay, so the first one is I have a continuous mapping now on a product. Okay, so it's a mapping from R cross S into T. Then I had this mapping, which maps R into the space of continuous mappings from S to T. First, you should check that it is indeed continuous. Okay, so in other words, if phi is continuous from R cross S, then this thing will actually take values in the space of continuous mappings from S to T. It may not, but it does. Okay, and it does it fairly easily. But not only is this thing well defined, but it's also continuous. If R has its normal topology, and this one has the compact open topology. Okay, I'll never talk about spaces of continuous mappings except with the compact open topology. Excuse me. Okay. Right, so that's the check map. Okay. What about the wedge map? Okay, so the wedge map, now it takes mappings from R into the continuous, so the domain so I start, sorry, with a mapping psi, which is a mapping from R into here. Okay, then I build a mapping, psi wedge, which is one of these ones. Okay, so it's a continuous mapping from R cross S into T. Okay. Now this mapping is continuous as a mapping from here into here, when R, the domain, the one of the terms in the product is locally compact. All right, so you see this local compactness condition coming up here, and I'll have some things to say about that. Okay, and then finally we have the dagger mapping, and the dagger mapping is continuous. Okay. All right. So we had the exponential law. So what does the exponential law look like in this setting of continuous mappings? So the exponential law started with R, sorry, R to the, T to the R cross S is, so let me get this right. So it's T to the S to the R, okay? That's just for sets, and we saw that that held for sets. So for continuous mappings, it looks like this, okay? So it's continuous mappings from the product and continuous mappings from R into the space of mappings. Because this thing is defined using the or involves the check and the wedge mappings, and we see that the wedge mapping requires local compactness. This thing is a bijection when R is locally compact. Okay, so not only is it a bijection, but it's a homeomorphism when R is locally compact. And so the tilde here means as topological spaces. They're isomorphic. Okay. So the exponential law here requires some conditions on one of the elements in my spaces involved. All right, so sometimes a bunch of spaces and mappings which satisfy this exponential law, sometimes this is called a Cartesian closed category. And Cartesian closed categories have many nice properties, and sometimes you want to make hypotheses that your space, the category that you're working with is Cartesian closed. But what we see here is, for us, that requires local compactness. Okay, so what are the implications of local compactness for us? Well, we're mainly interested at the end of the day in doing differential geometry. So talking about manifolds. And what does local compactness mean? Well, local compactness means that every point has a compact neighborhood, right? And so if you have a manifold, what does a neighborhood of a manifold look like? Well, the definition of the manifold topology is that it has a base consisting of charts, well, chart domains, okay? And a chart domain is mapped bijectively into an open subset of a locally convex space, right? So what that means is that on a locally compact manifold, every neighborhood so every point has a neighborhood which is homeomorphic to an open subset of a locally convex space, right? Um, and then the requirement of local compactness means that that neighborhood should have a compact closure, but you had a homework problem where compact neighborhoods imply finite dimensions, okay? So locally compact manifolds are always finite dimensional, and it's quite a severe restriction, and we'll see that comes up with the kinds of applications that you can consider later on. Okay. All right, so that's the compact open topology, and that's works for spaces of continuous mappings, right? So we can also talk about not just spaces of continuous mappings, but spaces of CK mappings, right? So we do this first for open subsets of locally convex spaces, okay? So I have two locally convex spaces, U and V. O is an open set. Then I have this space of CK mappings from O into V, and I define a topology for it. And the words that are involved in that definition are that it's the initial topology for this family of mappings, right? So what that means is that it's the coarsest topology so that all of these mappings are continuous. Okay, so what are the mappings? The mappings are just the derivative mappings. All right, so I have a K here, and I'm going to consider the derivatives dj up to order K. And then I have a mapping which takes CK into so it takes a mapping phi in CK and maps it to the jth derivative of phi. Okay, and as we know, if phi is of class CK, then this thing is continuous. Okay, so it's a continuous mapping with this as its domain and codomain. Okay, and so on this space now, this is a space C0 of continuous mappings. I use the compact open topology. All right, so the definition is that the CK compact open topology is the coarsest topology on here for which all of these mappings are continuous. So that's, those, if you're not used to those words, then those words don't have a lot of value. So let me maybe try to give some intuition for that. Okay, so the idea is, so again, a topology kind of tells you when things are close in some way or other. And so two mappings here are going to be close when their values and the values of their first K derivatives are close on compact subsets of this. Okay, so phi1, phi2, and their first K derivatives are close on compact subsets of these guys. That's the way you can think about the CK compact open topology. And you can include the case K equals infinity, and so define the C infinity compact open topology by not just saying that J goes from 0 to K, but you allow J to run over all positive integers. Okay, so that's the CK compact open topology. Right. All right. So one of the annoying things about all of this discussion is we saw that we are interested in mappings defined on products. Okay. Because mappings defined on products correspond to mappings into spaces of mappings. Right, so I have a mapping here into a space of mappings, and that corresponds to a mapping on a product. So mappings on products are important. So let me talk a little bit about those. Okay, first, let's take a topological space S, locally convex spaces U and V, and an open set O in U. The product I want to consider here is now S cross O. So S is my topological space, O is the open subset of U. Okay, and I define, so for a fixed X, I define phi sub X to be, right, so X is in S. All right, so if I fix the value of X in S, then it becomes a mapping from O into V, and it simply is, of course, that definition. I talked about that at the beginning of the lecture. Okay, and I'll say that phi is of class C0K, right? If it's continuous, okay, if when I fix an X, all right, so when I fix an X in here, it's just a mapping from O into V, all right? And so we know what to do with mappings from O into V. We can ask that they be of class CK, okay? So it's continuous in both variables. It's class CK and Y, but it's more than just that. If I fix X and take the jth derivative, okay, the jth derivatives are continuous as functions on S cross O. And so this is the usual domain of the derivative, but it's also a continuous function on S, okay? That's what it means to be of class COK. All right. So now, in this setup here, I had a topological space here. So really on topological spaces, I can't talk about differentiability in any way. But now I'm going to replace, and so that's why I have a 0 here, because all I can talk about is continuity for topological spaces. But if I replace my S with an open subset of a locally convex space, then suddenly now I have a function on a product, which is possibly differentiable in both elements of the product. Okay, so let me talk about those next. Okay, so my setting is U, V, W, locally convex spaces, N, open subset of U, O, open subset of V, and I have a mapping from N cross O into W. Okay. All right, so I'm going to take a K and an L. So these are positive integers, possibly infinity. And I'm going to say that phi has this regularity. Okay. So K corresponds to the first entry, and L corresponds to the second entry. Okay, so I'm going to define these iterated derivatives, drs. And so r is going to be some integer less than or equal to k, and s is less than or equal to l. Okay, and so this thing is going to take as its arguments x in n, y in o. Okay, then R elements in the vector space U coming from the R derivatives here, then S elements of the vector space V coming from these S derivatives, and I define it as follows. So what I do is I first calculate the S derivative of phi in the second variable, okay? Because S is sort of corresponds to derivatives in Y, okay? So I take the partial derivative in the second variable, S times, and evaluate that on these ones, okay? So then this thing here now becomes a function of X, okay? And as a function of X, I differentiate it R times and evaluate it on R copies of U, right? So that's what this symbol means. It means I first differentiate S times in Y and then R times in X. Okay, and then a mapping is of class CKL if all of these derivatives exist and are continuous. Right? And the notation you use for this is this this notation here. So CKL, right? So it's K times differentiable in the first argument and L times differentiable in the second argument. And these derivatives are continuous functions of all of their arguments, right? Okay. But it also makes sense to, if I have a mapping from N cross O into W, I can simply talk about CK of N cross O, sorry, CK of N cross O into W, right? I don't need CK comma, I can, N cross O is an open subset of the locally convex space U cross V. So what's the relationship between the CKLs and the CKs, right? So here it is. CK plus, so I fix the K and an L, and then CK plus L is a subset of this one. So everything which is of differentiability class K plus L is automatically CK comma L, all right? And then CK comma L are automatically have the regularity of the minimum of K and L, all right? And so in particular, this gives you the very nice implication that infinity comma infinity is the same thing as C infinity, right? So, and that's nice because infinity is a common uh, assumption that you make in applications, okay? All right, so that's just now spaces of mappings that we hadn't talked about previously. Mappings defined on products with different levels of differentiability in each of the terms of the product. All right, now we're going to define a topology for this one, and you do it in a way that's entirely analogous with what I did for just CK mapping as above, and that is you say it's the initial topology defined by all of these derivative mappings. Okay, and it has the same interpretation that these derivative mappings should be continuous functions of their arguments on compact subsets of the domain, and the domain is this. Okay. All right, so that's definition of the CKL compact open topology. All right. All right, so this now has just been me talking about mappings between open subsets of locally convex spaces. So differentiable mappings between open subsets of locally convex spaces. You can do the same thing for manifolds. Okay. So now we take M and N to be manifolds. And we want to talk about the topology for this space of mappings. So there's regularity things here that I'm not being careful with. And so, for example, if I want to talk about CK mappings, then both M and N have to be at least CK, right? This all goes away if you just restrict to everything being C infinity. Okay, so I'm a little there's some assumptions that are missing, but are easily filled in. Okay, so so what was the CK compact open topology in the local case? Well, it was the initial topology defined by the derivative mappings. Well, it's going to be the same here, but the derivative mappings are different. Okay, the derivative mappings are these mappings TJ that we talked about at some length. So the jth order derivative of the jth order derivative mapping. Okay, that takes a CK mapping to its jth order derivative. Okay, and you take the initial topology for these mappings for all j's less than or equal to k, and if k is finite, then you can just say it's the initial topology for tk, and you don't need to worry about 1 up to k, sorry, 1 up to k minus 1. And the reason for that is you'll remember that our definition of these T mappings contains all of the derivatives from 1 to k. All right. So as soon as you write down tk, you're writing down also t1, t2 up to tk minus 1. Right? But if k is infinity, then I have to take all of them. All right. And again, the implications are the same. So it means that mappings are close when their jth derivatives are close on here. Okay. Compact subsets of this. Right. So it's the same kind of interpretation as we had previously. You can also talk about mappings on products. Okay. So now I have Mn and P. Okay. And a mapping on a product. M cross N into P, and it's CKL. And so now I have these partial derivatives of higher order. Okay, so phi is a mapping from M cross N into P. So first what I do is I take the derivative of, oh, I think I mixed that up. Sorry, here, let me repair that. Check whether I did that right above too. Sorry, let me just make sure I did this correctly up here. Yes, it's okay. That one I have to make sure I do it right here. Sorry. Oh, sorry. This little square thing here shows up. No idea why, but I can't make it go away. The only way to make it go away is to restart this program. And of course, I end up. Okay, so let me go to where I want to be here. Apologies for this. I don't know why it started doing that in a recent update of GoodNotes, and it's not cool. Here. Okay, so yeah, sorry. I think I actually had it right, but I kind of feel like that might have been an accident. S R. Okay, so I differentiate phi with the second argument, holding the first argument fixed. Okay, S times, and then I take that thing and I differentiate it now with respect to the first argument R times. Okay, and I ask for the continuity of these things. So I look for the so I say that phi has class CKL if these things exist and are continuous. Okay, and then the compact open topology is defined in the obvious way so that these ones are continuous. Right. So TRS, okay, is going to take if R is less than K and S is less than L, it's going to take a CKL function and map it into a continuous function from here into here. Okay, and the definition of the CKL compact open topology on here is so that these mappings are all continuous. Okay. All right. All right. So now let's look at, so now we have topologies for all of the spaces that we need of differentiable mappings. Okay, so now we have all of our composition mappings, we have our evaluation mappings, we have our wedge and check mappings. Let's see which of those are continuous. Okay, so the composition mappings for fixed, one of the arguments fixed, those ones are continuous with no restrictions on M, N, and P. Okay. The joint composition mapping. Okay. So it takes a mapping phi here and a mapping psi here and maps it to psi composed with phi. Right, so that one's continuous, and in the for the compact open topology, we required the middle one, which was S in that case, to be locally compact, and in this setting, that means finite dimensional, as we've talked about. All right, so that's a big restriction now. Okay, so we only get continuity of the joint composition mapping in the finite dimensional case. All right, the dagger mapping. Okay, that's always well defined, first of all, and then continuous. The evaluation mapping. So again, for the compact open topology, for continuity of the evaluation mapping, we required the domain to be locally compact, which means finite dimensional in this case. All right, so M is finite dimensional, and then that one's continuous. Okay, all right, so space of mappings, manifold. Okay, now let's look at the particular case where the manifold P, okay, is going to be not just a manifold, but a locally convex space. Okay, so I'm going to be looking at mappings into a locally convex space, and I'm going to consider the check and wedge mappings in that case, and also we'll relook at the evaluation mapping there. Okay, good. All right, so so first of all, if we have a mapping, all right, so now we have mappings from products into something, okay? And then we're going to get a mapping from here into the set of mappings from here into here, right? So we get a mapping phi check, which takes a point in M and gives me a mapping from N into W. So if phi is CKL, all right, so K times differentiable in the first argument and L times differentiable in the second argument with continuity of the iterated derivatives, then phi hat is well defined, okay? And moreover, it is class CK. Okay, so why does that make sense? Well, that makes sense because this one is now a locally convex space, right? So, and the reason it's a locally convex space is because it takes values in a locally convex space, all right? And so this thing itself is a locally convex space. So I have now a set, I have a mapping from M into a locally convex space, and the locally convex space, it makes sense to talk about something with values in there as being of class CK. All right, so that's what I'm doing here. All right, so we needed for P to be a locally convex space to be able to make that statement, because we only at this point in time understand what it means to be CK first, this thing needs to be locally convex in order for this thing, in order for us to be able to say that phi check is of class CK. All right, so so that's why we're talking about locally convex things. And then similarly, phi wedge. Okay, okay, so phi. Sorry. Oh yeah, we're still talking about phi check. So this tells us that this thing is of class CK. Next, the mapping which assigns phi to phi, which assigns phi check to phi. That one is a homeomorphism onto its image. Okay. And if M is finite dimensional, then it's a homeomorphism. Okay. So this is the exponential law, right? So the exponential law says that there should be a correspondence between these, and that requires them to be finite dimensional. All right. So now we have the, sorry. One. So now I have the wedge mapping, and so the wedge mapping is always the more the better behaved one. So I start with a mapping from M, taking values in the space of mappings. And then the wedge mapping from the which is a mapping from the product into W. That one's always of class CK. All right. And then finally, the evaluation mapping. Okay, so I'm going to now look at mappings from M into W. Okay, so that one is a locally convex space. All right. And so I have a mapping to find out a product here. First argument is a locally convex space. Okay. And this one, it turns out, is of class C infinity K. Okay. And the reason that it's C infinity in the first argument is that this mapping, which is the evaluation mapping, it's linear in phi. Okay, so it's linear in the first argument. And so we kind of know that it's in continuous linear in phi, and continuous linear mappings are automatically C infinity. So that, roughly speaking, that's why this thing is C infinity, regardless of what the regularity is here. Okay, so what have we done so far? So let me summarize. So we talked about mappings induced between spaces of mappings. We talked about that first as for sets, for topological spaces, for open subsets of locally convex spaces, and for manifolds. Okay, and various of those induced mappings require some hypotheses to be continuous or differentiable. Okay, what we haven't done, and so here we had to do a kludge, right? So in order to talk about mappings into this thing as being of class CK, as we did there, we needed for this thing to be a locally convex space. But what if so we need and therefore we needed W to be a locally convex space. But what if W is not a locally convex space? Can we still put a manifold structure on here, which would allow us to say that a mapping like this is of class CK? Okay, but now this thing now needs to be a manifold. Okay, so that's what we want to do now. Okay, so we start with a smooth compact manifold, right? So C infinity. And a finite dimensional manifold M. M doesn't need to be finite dimensional for this construction to work, but it does have to have some hypotheses, and I don't want to talk about what those hypotheses are. So those hypotheses hold when M is finite dimensional. And that's all we need for the examples that we're going to talk about later. Okay, so what we're trying to do is put a manifold structure on here. I'm not going to tell you what the charts are for this manifold structure. It's a little bit complicated to put that all together. But I'll just tell you what the punchline is. The punchline is, so remember, K is the regularity of M. Okay, so this space of mappings has a CK differentiable structure, and the CK differentiable structure has a list of properties. So first thing is that if I take some other manifold N with some regularity, CL, okay, and I take a mapping from N into my space, which I'm now trying to turn into a manifold, okay, then this mapping is of class CL if and only if its check mapping is of class CLK, all right? So, you know, that there's a lot of, so have I even said anything new, right? It's not really clear. The thing that's new here is that this is now a manifold, okay? And so this is saying that as a mapping from this manifold into this manifold, and it's the differential structure of this thing that I am asserting in this statement, is such that CL-ness of this mapping is equivalent to CKL-ness of this mapping. Okay, that's one property. The other property is, so we've seen this property above for the evaluation map. Okay. A property, and in our discussion for the evaluation map here, we needed for this space to be locally convex in order to make this statement. Okay. But now what I'm saying is there's a manifold structure on here, which again makes this thing of class C infinity K. All right. So previously we had the locally convex structure, which allowed us to assert the C infinity K-ness of the evaluation mapping. Now we have a manifold structure on here. Okay. Manifold topology. So we have seen that if you have a manifold, it induces a topology for your underlying set in a natural way. So the base for a base for that topology is just a set of all charge domains. Okay, so every manifold has a topology. The manifold topology for this is exactly the CK compact open topology. Right. Another property is continuity or CK-ness of this composition mapping. So now I take two, um, uh, and so I say locally compact manifolds. That really means finite dimensional. So I'll say finite dimensional. Okay, so two finite dimensional manifolds of regularity CK. All right, and if I have a mapping from M1 to M2, okay, then I have this induced mapping from CL MM1. All right, so this now has a manifold structure, okay, because that's what I'm describing in my statement. This has a manifold structure, and the statement is that this mapping is of class CK. All right, so that again, I'm not telling you how to build this manifold structure because that's it's not necessarily that difficult, but it's a bit of a project. Certainly, I wouldn't have time in a lecture like I'm giving right now to say how to do that. Okay, now I made a big assumption at the beginning of this discussion, and that is that K is compact. Okay. So that assumption turns out is required. And the reason that it's required is that if M is sorry, sorry, if M is not compact, then you cannot put a manifold structure on here for which the manifold topology agrees with the compact open topology, right? So that's a non-existence statement. And so what that means is that if you turn this thing into a manifold, its manifold topology will be some other topology than the compact open topology. That may be fine, but to my from my experience, this is a major drawback of the theory of spaces of manifolds of mappings, because the any kind of manifold structure you put on here has some drawbacks. Okay, and there's reasons why those drawbacks have to be there, but nonetheless, there's drawbacks. Okay. So it's also possible to describe the tangent spaces of these manifolds. So let me take a mapping phi in here, right? So this is the thing whose differentiable structure I just asserted the existence of. What I want to do now is define the tangent space to this at that mapping phi. And it's simply, sorry, I should be a little bit more careful about this. Okay. So the tangent space is canonically identified with the following set of mappings. So it's the mappings of class CK from K into TM with the property that the tangent vector in TM that gets assigned to a point in K, right, that's x of x, is in the tangent space at the point phi of x of m. And if you sort of go back and you look at our definitions of pullback bundles, you see that the tangent space is exactly the pullback. The tangent space at phi is identified with the pullback bundle. Okay. So that's nice. You get an explicit description of what tangent spaces look like, and therefore of what tangent vectors look like. And we're going to use that construction here in a second. Okay, so I'm going to finish the course by talking about two important applications of all of this machinery that we've been talking about, and specifically that we've talked about today. Okay. The first is called, and these examples are not going to be treated in any detail. I'm just going to sort of tell you how you frame these things using the machinery that we've developed, and certainly not give you any precise formulations. Okay. All right, so the first thing is what's called shape analysis. So I'll tell you in a second why this is called shape analysis, but the idea is this. I have a compact manifold K, and it has what's called a volume form. So we talked about differential forms last time. So if K is an n-dimensional manifold, a volume form is a degree n differential form that doesn't vanish anywhere. So if you've never seen differential forms before, the words that I just said have no meaning for you. Okay, but that's what a volume form is. And an M is a finite dimensional Riemannian manifold. Okay, so now I just told you in the preceding discussion that this thing is a manifold. Okay, and moreover, I can turn it into a Riemannian manifold, and it turns out to be a weak Riemannian manifold. So we talked last time about weak and strong, and so here I just said Riemannian manifold, and I didn't tell you whether it was weak or strong, and because it's finite dimensional, it's strong. Okay, so I said last time that it's I think I said last time that finite dimensional manifolds are automatically all Riemannian metrics are strong Riemannian metrics. Okay, but we're going to induce one on here, which is not a strong Riemannian metric. Okay, and here's how you do it. So I'm going to call this thing like that. Okay. And so what does a Riemannian metric do? It takes tangent vectors at a point and takes their inner product. So here's what I take: tangent vectors x sub phi and y sub phi. So these are tangent vectors at the mapping phi. Okay. And so now if I evaluate x phi at x and y phi at x, I get these are both in the tangent space at phi of x m, right? That's what I just told you about tangent spaces. Right, so then I take their inner product with respect to the Riemannian metric on m. Right, so this thing now will just be a number, and then I integrate over k. Right, so that's how you can build a Riemannian metric on here corresponding to a Riemannian metric on here, and a volume on there. All right, so what do people care about in shape analysis? Well, you have your K, and you think of phi K as being a shape, right? And so as I change phi, the image of phi of K under phi will change, and you can think of that as being change of shape. And so in some manifestations of this, if my compact manifold is, say, the circle, and my codomain manifold is R2, okay, then what's the shape going to be? Well, I take the circle and I map it under phi, and I get something here, and this is a blob. It's supposed to be like some sort of facsimile of a human. So if I change the mapping phi, I change what the blob looks like. Okay, and you normally want to put some restrictions on things, so you want to maybe make it so that the thing doesn't have self-intersections, because Humans don't have self-intersections, for example, and you want to make sure that it has no sharp corners like this one does. Okay. And so you have to make some assumptions about the space of mappings that you deal with to prevent stuff like this from happening, but you can go ahead and do that. Okay, so this Riemannian manifold turns out to not be so bad. Okay. In the sense that, for example, it possesses a Levi-Civita connection. Okay. But in shape analysis, what you would like to do is you really only care about the shape, right? That's why it's called shape analysis. All right. Now, there might be many mappings phi which give you the same shape. All right. And essentially, the mapping phi doesn't just give you its image, it also gives you a parameterization of the image. And so you maybe are really only interested in the shape, not the parameterization by the specific mapping phi. And the way people deal with this in practice is they perform a quotient. Okay. And the quotient is by set of all diffeomorphisms of the domain manifold. Okay, so that way, two mappings here which differ by a diffeomorphism and which give the same shape, you regard those as being the same. Okay, so it's kind of quotienting by parameterization. Uh, uh, So yeah, so Bianca has the question, why are compact open topologies coarse? Well, the reason is this. So all right, let me answer your question. And to do so, I will go down here. Okay. Um, so what is in some sense the coarse? Let's say I have a mapping on this space. Okay. The coarsest kind of topology that I can put on this is what's called the pointwise convergence topology. Okay, and this is the topology whose pointwise convergence. Okay, and so the base of open sets, or the subbase of open sets for this topology is now going to be, so I had this collection of things which I defined before as M, and here I had a K, but now I'm going to put an X, okay, U, okay, and this is going to be the set of all mappings phi from phi in C0 ST such that phi of X is contained in U. All right. So now, when are two mappings here close? Well, they're close if their values at X are close. Okay. So really, this topology, it's only evaluating mappings at X, and it's just saying mappings are close when their values at X are close. So, they could be close at X, okay, but immediately adjacent to X, they could be very far apart. Okay. Now, the compact open topology is sort of the next in line because we replace the points X with compact sets K. Okay. So compact sets are not that far removed from being points. So for example, every compact set is a finite union of neighborhoods of some finite collection of points. Okay. Um, and so the next in line, so this is going to be very, very coarse. One way to think about coarseness is that it has lots and lots of converging sequences. So a sequence in this topology converges if and only if I take the mappings and evaluate them at X, so phi of X, that sequence converges. Whereas in the compact open topology, I have to get convergence over all of K. right? So it's a little bit better, but it's only over compact sets. What you would maybe like is you would maybe like to consider, something like where the subbase is S U, okay, where this is phi in C0 S T, where phi of S is contained in U. And so what this means is the two mappings are close in the topology, that has this as a subbase if they're close over all of S. Okay, so we have closeness over at just points, we have closeness on compact sets, and then we have closeness over all of X, right? So this sort of goes from coarsest, intermediate, but still actually quite coarse, into a topology here, which is quite fine. Okay, so this, the open sets here, and in some sense, this is the topology that you might want to use, right? Because now you're saying the two mappings are close when they're close over the whole domain. But that's not what we're doing here. So off of the compact set K, they could be very far apart. Okay, so yeah. All right, that's a good question. Thanks. Okay, good. Resuming. What am I doing? Right. Okay, so we were talking about shape analysis. So as I said, in shape analysis, sometimes what you do is you quotient by diffeomorphisms of K in order to remove the parameterization. And then when you do this, there's some sort of Riemannian manifold that you get from quotienting. And the difficulty is that that Riemannian manifold is quite ill-behaved in the sense that the Riemannian distance between two shapes will be 0. Okay, so so when people do shape analysis, they spend a lot of time kludging to get around this drawback. Okay, and that's all I'm going to say about shape analysis. So there's tons of papers out there about that if you're interested. Okay, another kind of application is what I'll call evolution equations. And so again, let's sort of talk a little bit in general. So I have a compact manifold K, a finite dimensional manifold M, and an evolution equation. So I'm not going to be super careful about what an evolution equation is. I'll just give a couple examples, concrete examples. But essentially, an evolution equation gives me a time evolution for mappings in here. Okay. So I have a time-dependent family of mappings from here, from K into M. All right. And so, in shape analysis, maybe I might have a family of shapes that are, sort of smoothly parameterized by time as I go from one shape to the other. All right. But here's two examples of the kind of thing that I have in mind for this. The heat equation. Okay, so the heat equation is a common partial differential equation. So here I'm going to take my compact manifold K to be the interval 0, 1. So we haven't really talked about this as a manifold because it has boundary, but you can deal with the boundary and it's not a big deal. And I don't want to make it into a big deal. All right, so that's going to be our domain manifold, and our codomain manifold is going to be R. Certainly, that's a finite dimensional manifold. And in the heat equation, you think of C infinity mappings from this interval into R as being a temperature distribution. So the heat equation is describing a temperature distribution of a rod, and the rod has length 1 here. And R is measuring the temperature as a function on the interval 0, 1. Okay, so there's an equation which governs temperature distribution, which is called the heat equation. And so here's the heat equation. So this is the one-dimensional heat equation. So the temperature U is a function of two variables, T and X, and and the temperature satisfies an equation like this. Right? And so here we think of the temperature U as being a function of two variables, T and X, as I said. T is maybe non-negative, X, as we've already said, it lies in the interval 0, 1, and it takes values in R, which is the temperature. Okay. So when I write down this equation, I have partial derivatives of u in t and x, right? Because this is a function of two variables. What I can instead do is consider the check of this, okay? And the check of this says now, as a function of the first argument here, which is t, okay, I have a mapping from the interval 0, 1 into R. So in this sort of formulation, I have a time-dependent family of mappings, right? So that's an evolution equation, a time-dependent family of mappings. And what does this equation look like when I use this representation? Well, it literally says this. It says that I take this mapping, which, right, time into here, and I d by dt it. Okay, so take its normal t derivative, right? So this is a curve, right? Then, right, so that corresponds to this one. Okay, and then sorry. I put that minus sign there. And that is equal to my k, and then I have a of u check. Right. So what's a? So a now, so u check of t is a mapping in here, and a of u check of t just takes it and differentiates it twice, right? So the differentiation is a function on 0, 1, so that's x, right? So that's how this thing corresponds to that. And so what it does is it takes a partial differential equation, right? So an equation in two independent variables, but a finite dimensional codomain. Okay, so independent variable is just R. Sorry, the dependent variable is just R, and changes it into something with a single independent variable, but the dependent variable is now infinite dimensional. All right, so it trades off a partial differential equation in finite dimensions to an ordinary differential equation in infinite dimensions. Okay. And again, I'm not going to say anything about what you can do with that, but that just, and so, we see how our, check and hat mappings show up here. Okay. All right. So this is a kind of trivial thing, and this certainly isn't, if you were teaching a first course in partial differential equations, this wouldn't be the approach you would use to look at this equation. You don't want to consider this infinite dimensional manifold of solutions. Okay, so it's kind of overkill for what you do with the heat equation, but here's a less trivial example. I suppose I have a finite dimensional Riemannian manifold, okay, and I want to consider the set of diffeomorphisms. Okay, so this is going to be the set of infinitely differentiable diffeomorphisms. So this is the subset of C infinity mappings from K to itself, which are bijective and have an inverse that's also C infinity. That's what a C infinity diffeomorphism is. Okay, so you can prove, it takes some work, but you can prove that this is an open subset of this one. Okay. And Euler's equation has to do with fluid mechanics. There's all kinds of related problems that are connected quite intimately with the kind of thing I'm talking about here with Euler's equations, but I'm going to think about Euler's equation as describing the motion of a fluid. So the idea is that I have a fluid which is occupying my manifold K at time t equals 0, and then at time t, I have a diffeomorphism. Okay, and what that diffeomorphism does, so I have my two copies of my compact manifold here, and I have some points which occupy this compact manifold, which are the points in the fluid, and each of those gets mapped to some other point by phi of t. Okay, so phi of t kind of describes the motion of the fluid particles. All right. So the normal way you represent the Euler equations is you don't work with phi directly. You work instead with the velocity field, and the velocity field is defined by a formula like this. Okay. So I have my diffeomorphism phi, and I describe a mapping U, which now takes values in the tangent bundle, and it's essentially the derivative of phi, but you have to keep track of where you're evaluating. Okay, so U is like the fluid velocity, in other words. Okay, so with this definition of U, the physical equation that describes the fluid motion is what's Euler's equation, and so I've rewritten it here. So this is the Riemannian covariant derivative that we talked about last time. This is the gradient of P. P is a pressure field, and the pressure field is there to maintain the, so I'm talking here about incompressible motion, I should say. I forgot to mention incompressible, which is important. So it preserves volume. So if I take a little chunk of fluid and I map it under the diffeomorphism phi, I get some, maybe distorted shape, but it has the same volume. Okay, so it's incompressible. So this is this is just the divergence free means exactly that it's incompressible. Okay, and P is the pressure field which maintains the incompressibility constraint. So P has to be solved for as part of the solution of the equation. Okay, so the theory of fluid mechanics produces Euler's equation. And if you've never seen Euler's equations before for fluids, what I am saying now is definitely not going to help you understand it. And if you have, maybe this will look familiar to you. Okay, so now, sorry, I'm running a little bit over, but I won't be too much over. And I'm going to blame Bianca because she made me talk about compact open topology. So there's a significant theorem here, which was one of the first theorems in sort of this kind of analysis, which is due to David Eben and Jerry Marsden in 1970. And what they showed was this. Work now with a space of volume preserving diffeomorphisms, because we're working with incompressible fluid flow. Okay. What it says is that, so we have this correspondence between diffeomorphisms and these velocity fields. Okay, so the velocity fields satisfy an equation like this. The diffeomorphisms satisfy are governed by some geodesic equations. And here's what the geodesic equations are. So the Riemannian metric that I'm going to use on the space of smooth mappings from K to itself is exactly the one that I defined above. Okay, so when I talked about shape analysis. So when I had shape analysis, I defined this Riemannian metric. Okay, and this needed a Riemannian metric on M. So remember, K and M here are the same. Okay, so K is a Riemannian manifold, so that's where G comes from. Okay, so I need that. And then I also have a volume form here, but it turns out on a Riemannian manifold, well, an orientable Riemannian manifold, there's always a volume form. Okay, so a Riemannian manifold also defines mu. Okay. And so the major theorem of Eben and Marsden is that there's a correspondence between solutions of Euler's equations, okay, and geodesics on the space of volume preserving diffeomorphisms. Right? And now this is very much a non-trivial statement. So I've sort of included a trivial example, the heat equation, and a non-trivial example. And that's the end of the course. So that's it. I'm of course free to meet between now and whenever the course ends, which is probably when I assign the grades after the final homework is due. And if you want to chat, we can certainly do that. But I'm finished with the formal lectures. Thank you for your attention.